Ladies and gentlemen, let us reconvene. As I said before, I'm sure that the presentation sparked many questions, and first person to get to ask them is Joanna. So reluctantly, I will hand over the microphone to you.
Thank you. I'm not sure.
It is towards the...
Great, good, just check in. Thank you for a nice presentation. I appreciate your illustrations. They help to clarify a few things. I thought of starting off with a question I know you can answer to. And I was curious why you started working in the railway domain and with these things.
Well, I previously, before this PhD, I was working in railway operation already in a railway company, and I could see from operation there was something that could be done to improve the operation. And especially I could see really what guided me was actually what brought me to the last paper. So there were evidently recurrent delay patterns. And I wanted to find ways to show to the... I was working in a train company, and there was a continuous negotiation with the infrastructure manager. And what I wanted to do is to be able to prove to the infrastructure manager that they were doing something recurrently that should be improved. So yeah, eventually this led me to study how to improve the delays. So it's more a personal interest in railways and in railway operations specifically.
Okay. So then to my first, little more tricky question. You use, I was lacking a little bit the introduction to very important terms in your thesis. So I would have liked to see definition of what is a disturbance, because you use both disruption and disturbance. Do you find that they are equivalent, or have you? Well,
I would say that there is not a defined definition of this. Like in literature and also in operation, you can find different people using the same terms for different meaning. What I would say that is that usually disruption refers to larger events. So, for example, a snowstorm or a breakdown that stops many trains and generates higher delays. Whereas disturbances refers more to little deviations from the schedule. This is the difference that I might say. But you can easily find people that refer to either of the two using the other term. And this is also in railway air traffic or other means of transportation.
Okay. So you handle both with your research?
I handle more, I would say, these disturbances.
Okay.
So something that happens in every day, which has to do with stability and robustness.
Okay, good. Because I also think disruptions are a lot more severe, and I didn't see how your models could handle that. But we come back to that. You also have, you say that delay recovery is stochastic. Do you really mean that it is stochastic, or do you think that there are factors that you have not yet explored?
Well, I would say the second. In particular, it's not stochastic. There are factors that have influence on this. And these factors are of different natures. There can easily be congestion that has a strong impact on the possible recovery. But there's also stochasticity in the behavior of the train driver. So there can easily be everything free ahead, but then the train driver has a driving style that is lower, or there could also be variations, which I would say are stochastic, looking at these factors. On the performances of the individual rolling stock. There can easily be one of the engines that doesn't work. I would say we do not know enough in any specific case to call it. We cannot say that it's not stochastic, because otherwise it would require us to have a much broader knowledge that we cannot afford.
No. The question, why I pose the question is that if there are so many elements that are stochastic, it doesn't give us much hope. Right, to fix things, right?
There are some that we can cope with.
Yeah. So I would like to go over to the first paper, part A. You are mentioning shrunk analysis, and I did not know what that is. So can you explain that to me?
I guess you mean here in the with the skimming method, right?
Yeah. So you use the term shrunk analysis as if it's something common in the paper. Is that a common term?
Well, this paper is 4 years old. I would say that maybe the terms are not exactly correct or not exactly placed. I would say this is more a sampling approach now that I know better the field. Okay. Because what we do is to shrink the domain of simulations. So this is what I mean by
shrink. So it's sampling.
Yeah.
Yeah. Okay. No, I thought I have missed something. And you also mentioned that there is, of course, a time gain by using the skimming method. And you say in percentage how much you gain, but you never discuss any running times, any real computation time. So what is the computation time we're talking about? I thought
about including this in the presentation, but there was not really so much time. I would say that in this specific case, one individual simulation would take up to 1 minute. Okay. So if we wanted to run an individual simulation for every possible value of a primary delay, for any possible train to be delayed at every possible station, that it would result into thousands of simulations. I made a calculation some time ago. It was about 5,000 simulations. That would require 5,000 minutes then. So for every scenario, we had 5 scenarios. So we are multiplying time by time the running time.
And what do you lose then in accuracy? You had some discussion about it, but I wasn't really. When you sample, you say you get the same conclusions, more or less.
Yeah. At this starting point, there was not an estimation of the loss in accuracy, and that was based on the assumption that since the difference in the aggregate line delay between using one train and the overall average effect would be the minimum possible. I would say that in the following paper, when the technique was a bit more ready for use, we changed a little the mindset. Instead of sampling, like looking just at one individual function of railway delays, we used the averaging of the whole effect. That means that in this case, if there is some train like this one that has extreme effect, which is exactly this one, we cannot see this if there are even more, because we are only simulating one. For this reason, in the second papers then, in the evolved papers, we actually take into account all of them, and we average them, including the probability that actually we should be looking at that specific curve or function of aggregate line delay.
Mm-hmm. Would you think of any other ways with modern technology to speed up, rather than doing sequential 5,000?
Well, if we are considering specifically the technologies, we can increase the computational power, or we can use parallel computing to compute this. Like it is a general knowledge that the computational power grows exponentially with the time. So I would say that maybe in some years we will be able to simulate everything, even including this in optimization models.
And the OpenTrack and Railsys are more prone to also explore these.
Yes.
Yeah, because they are not really.
I had the chance to compare the use of both the systems in this PhD project. Mm-hmm. So I would say that Railsys performed faster in all the cases that we studied. But on the other side, it's also true that OpenTrack has a more detailed explanation of the exact formulation that are used that backs up the research. So it is easier to justify the result or to analyze the results, because you know every exact calculation that is going on in the system.
Mm-hmm. Okay, I also have a question. The first paper is the only paper you are the sole author of.
Yeah.
Right? So I was just curious. Often it's the opposite, that you start out with co-authors and then the last paper is your own.
Okay.
How come the first one was?
This was based on some other experience that I had previously from TU Delft.
Okay.
And this is also one other reason why it is based on the Dutch railway line.
Mm.
I had performed the simulation. I knew very well the case study. And then I actually found quite some help from the supervisors that are all the co-authors in every specific paper, which all contributed in specific ways in the paper. So it was more broadening the collaboration throughout the research.
Okay. Then we move over to paper 2. Here's also you're discussing the trade-off between computation time and accuracy. And you say that the main things, you are simplifying the train interactions, right?
Yes, so here.
Yeah. So I was wondering, do you think it's an optimistic or pessimistic prediction?
Well, this is a tricky question.
Yeah.
It depends. I think that on average, it's on the target, and it can either be pessimistic or optimistic, depending on the individual case study.
So what would you say would be let's say the dispatching strategy? You assume here FIFO, right?
Yeah.
And they're not allowed to overtake?
Well, in this case, I would say that there's the FIFO in the junctions. Whereas in the diverging lines, there's not an issue because there's not a conflict in the train trajectories that are combined. Whereas in the other one, we are actually assuming that the order in this specific case in junctions does not change. So you're right. If you make me think about this, I would say that dispatchers will instead apply some strategies to reduce the delay. Yeah. Which is not the case if we consider specifically the case where we have the divergent points here. If we have the opposite situation of this, then of course the dispatcher will choose what is the first train that should pass to reduce the total or the general effect of the delays. Not always, I would say.
Yeah. So pessimistic in
this is
this
the
case.
pessimistic
Yeah.
evaluation, I would say.
Is the FIFO applied in reality in these contexts that you've been studying?
It really depends on the strategies of the train dispatchers, or better to say, on the traffic ruler. There are cases from my experience in operation where no matter what, the train order will be preserved. Can even be 10 minutes of delays. There will be no order swap. There are other chances where some operators can even be helped a little by the dispatching choices, where the strategies point a little more on preserving the performances of specific trains.
Okay. And so would you say that it's easier to analyze the behavior of the dispatchers when you have a unidirectional lines? So is it easier to follow and isolate that?
Well, you mean when we have some junctions? Because if we have a railway line which is unidirectional with no junctions, that there will be actually no dispatching choice. So if we are looking at diverging lines or where we can have some dispatchers, some dispatching, well, I would say that it's not easy to model the dispatching rules. And this is because dispatching is still demanded is still a task given to people, and you should model the discrete choices in the operation, and it's not necessarily driven by these decisions are not necessarily driven by a clear target. It can be just driven, for example, by expertise, by personal experience, which is very much the case in railways.
But that means that it's difficult to validate, to compare reality with a simulation model.
That's also why most of the models are usually compared to simulation models, because in simulation models these are protected environment where we know exactly what is the input and we can estimate the output, and also because we know exactly what are the primary delays that we are assigning, and we can measure the relationship. In operation, there are so many different aspects that overlap. So different primary delays or primary delays that affect multiple trains at the same time. There can be different conditions for the weather, different adherence on the track, passenger flows. Simulation models are easier to select the effect that we are looking for.
But it's difficult to convey the conclusions with practitioners, I imagine.
Yes.
Then,
That's also one of the reasons why the application of research results are hard to implement in real operation in railways, and also why it is always a little behind the other methods of transportation.
Yeah. I have a question about then paper 3, where you say that you look at heterogeneous systems, right? And in section 3.2.5, and you state some assumptions. I need to find it myself first. You say in the conclusion part that under this paper derives a total delay under the assumption of equal buffer time between trains and equal running time supplements over the line. To me, that sounds like a homogeneous system, not a heterogeneous system.
Yes, maybe it is a bad word choice. It means that the analytical model, which this heterogeneous model is based on, considers an approximation towards equal buffer time and running time supplement, which is how the individual relationship between aggregate line delay and primary delay is calculated for individual trains, for the trains that we delay. And this is how the single functions, these functions are calculated. So it refers more to the calculations of these functions, these two. Okay. In that case, we are assuming that A and B, these two parameters, are equal throughout the timetable. The point is that for these heterogeneous timetables, A and B will be different depending on the train that received the primary delay.
So you still assume equal?
Yes.
Okay.
It is. I mean, it is not really equal in the timetable. It is an approximation in the analytical model.
Okay. I think I leave over to John now.
Okay.
Thank you for your answers.
Thank you.
Well, thank you very much for your presentation. It was obviously a big challenge to get the details of 5 papers into 45 minutes. So I'd like to start off by actually asking you a question again about paper 3 and actually the run-up towards the graph on the right there. Not on your presentation and your, your thesis.
Okay.
You didn't mention this in your presentation, so that's why I'd like to ask about it. So, version 2 of your thesis, I don't know whether you've got that with you. I'm referring to page 103.
Okay. Yes.
And so here on in the middle paragraph here, you're saying, we regress the related total delay developed on the line to individual functions for every delayed line. And over the page, At the top, you're saying the total delay general function of the railway line was regressed from the whole set of simulations and compared to the combination of the individual delay functions. But in your presentation, you didn't talk about regressions very much. So could you say a little bit about how many regressions you did, what was the goodness of fit, etc., etc.?
Yes. So what we did in this point is that at this point of the research, the A and B are we developed the method to estimate the approximation of A and B to be equal in the functions only for the homogeneous timetable. That means that we took some weighted averages of the available A and B in the timetable, something that we could calculate. But this buffer time between trains changes over the stations if we are looking at heterogeneous timetables, and so does the supplement time. It is different between different train paths if they have different stopping patterns. So we do not have at this specific point, an analytical method to estimate this A and B. So to overcome this limitation at this point, what we did was to simulate these color dots that are simulate individual values of, or there are selected values of primary delays, and to estimate or to measure the aggregate line delay from these simulations. So we simulated primary delays to either train A or train B. Now, at this point, we could deploy the functional relationship found from the previous paper, which is a polynomial relationship, and we regressed these points towards a cubic formulation because we knew that in these cases the delay would be always recovered within the study domain that recalls in the analytical delay model to a third-degree polynomial relationship. So what we could do is to identify the parameters with inversion of those polynomials that were found by regression, and then we could then average the values from the two regressed curves using the weights from the probabilities, and then identify the final curve as a function, as a polynomial function that resulted from the regressions.
Okay, and how statistically robust were those regressions, though? Because you don't have any of this.
Well, we compared. It is not. It is not stated neither in the paper, neither in the presentation. But we also we simulated also random delays on the line without assigning a specific train. And this is actually where we got the influence of the incident. So we defined some incidents that were blocking the operation, given some characteristics of starting time, stochastic uniform starting time, and uniform duration. And then the result was quite close to the point. There's not a goodness of fit measure now.
Okay, and then also relating this, just go back and explore the assumptions underpinning a lot of this work, which are stated with respect to paper 2, I think back on page 57. And I think to some extent you've answered this with respect to paper 3, but I'd still like to explore this if I could. So you're saying here that the line you're requiring one additional simplifying hypothesis is necessary to calculate the settling time. The line consists of equitemporal line segments and identical train dynamic performance, etc. How restrictive are those assumptions? And I know you do relax them a bit later on in this particular paper. I just wonder whether you could comment on that, please.
Well, as I mentioned, this paper is focused more on the aggregate delay. So both this measure of settling time is more on the side of that research. So it's mentioned because it is relevant, but it's not analyzed in detail because it is remanded to another. It is recalled to a further research. In particular, we use this assumption is restrictive in the same way, the assumptions on equal A and B are restrictive to the model, so, or these are assumed to be so. So we can calculate, for example, an average equal running time for all the equitemporal sections and occupation of the blocking sections, which can result from, for example, averaging out all the different sections between the timing points in the model. This is not explored yet. So this could be the methods to find these equivalent values of equitemporal headway and running time between timing points should be addressed. One thing is that another approximation that is not, I don't recall whether it is mentioned here, is that this formulation is on the maximum, takes the maximum between two individual points, between the time that it takes for the recovery train to pass the station or to the first train to reach the recovery station. This is an approximation from the discrete case which we are using to the continuous case. In fact, if we were looking at the discrete case, it was actually not true. It would be not true that it is only specifically on one of these 2 points. And this is because this is all linear, so we can say that the minimum is on one vertex of this polyhedron. But if we had it in the continuous form, then we would have to consider all the possible combination across this recovery region, the border of the recovery region. We assumed at the beginning that the variation between the solution on the line or close to the line would not be so different from a solution that is actually on the edge of this polyhedron.
Okay, thank you. Now, I guess another challenge you had in presenting all your material is I think you had at least 4 case studies in 2 different countries. Can you just say a little bit about the rationale for these choice of case studies? Why these particular 4?
The first case, as I mentioned before, was given. Apart from the reasons that I said in the presentation, it's also because it comes from simulations already available from another environment, and that was already a good fit for the research. And plus, we also got industrial partners for the IPTOP project that were in the Netherlands. So it would be an easy catch. And also, overall, in the IPTOP project, at the beginning of the project, we wanted to benchmark Denmark with other countries. That's also one reason why we want to simulate other countries, or we didn't find it really an issue. Then the choice of the other case studies. First of all, we have the suburban railway line here, which is for the analytical delay propagation model, which is used 2 times. And that was chosen because there's also a lot of studies, also in other projects. For example, there's Robust Rails that was focusing a lot on this suburban railway line. So we had already the knowledge to build some models, some simulation models for this line. And plus, we also followed basically the main interest of the institutions and of the industrial partners, which are Bene Denmark, DSB, and the Traffic Directorate. So it was also influenced by the interest of the partners. And lastly, and this is even more the case, the 2 case studies for the data analysis were really driven by the interest of the partners and of the public. The coastal line is been under the spotlight of the public audience for many years because it has had a very low reliability for many years, and it has changed over time. Very many different operators, because they were not making it to get reliable. So there was some interest from both Benchmark and DSB to find methods to improve the reliability. I can mention one of the results was actually confirmed also by DSB. One of the clusters of the delay change profile of delay increases. Sorry for your rush. This, in particular, this cluster was actually also confirmed by DSB, and this is because at this station we have a junction from another separate railway network that is powered on diesel train, completely independent from the rest of the network, apart from this the stretch between Snekesen and Elsinore. And this is visible in these delay patterns that are evidently linked to some conflicts of circularism that were generated on this specific timetable, which this is from 2014. And they confirmed that the punctuality related to this was increased in the last timetables because they increased the headway between trains conflicting at this station. So there's also some evidence that this, apart from this method, they could identify some specific processes that should be improved.
Okay, thank you. You've mentioned that you use OpenTrack a lot in particular papers 2 and 3, and you've explained some of the strengths and weaknesses relative to its main competitor, RailSys. My question is, for your case studies, how well validated is OpenTrack itself? So to what extent does OpenTrack give you the ground truth that you're really able to compare your analytical models against? Well,
OpenTrack is very largely used in both research and in the industry. I would say that, to my knowledge, it's a little more used than RailSys from the cases that I know. So I would say that its fame itself would be enough. And plus, OpenTrack provides all the individual formulation for the calculation of the train dynamics, which of course are an approximation. These are models, but at least in this case they are provided. So you know exactly what every train is modeled to do what at every point of time, and you can even tweak these parameters. You have the power to modify the behavior of the trains, and you can even introduce some stochasticity in the train driver's behavior. To my knowledge, this is not given in RailSys. RailSys is much faster, but on the other side, it's more like of a black box. Like you do not know how the individual train performances were calculated. You do not know how the resistance, for example, is calculated at every time. So it's a little more tricky to defend the result that come from RailSys from a scientific point of view rather than OpenTrack.
Okay, but what I'm driving at is not so much OpenTrack v RailSys, it's simulated data v real world data. Because your simulations are for lines A and E. Yeah. But your real world data is for other lines in the Copenhagen suburban network. So my question is, how well does OpenTrack simulate actual delays on lines A and E, and were you able to look at that?
Well, that's a good question, of course. Well, that depends on how we simulate the delays. First of all, we are not simulating how delays come into generating in reality. We are more simulating in these OpenTrack models the relationship between a known primary delay as compared to the extent of the effect of these delays. So we can take the stochasticity of the delay generation out of this part. So we can, I would focus rephrase the question if it is allowed to, how do we ensure that the interaction between the trains or the conflicts of circulations are well modeled. Do you agree on this?
So rephrase that again?
Well, I would say it's hard to compare to reality. Even if we were looking at the same railway line, it would be hard, because in reality you don't have just one primary delay that you can simulate, or you don't have one primary delay and you can measure where you can measure the effect of. You have many different phenomena there are overlapping, and you cannot split or separate the effects of individual primary delays. You should really be lucky to find one day where you only have one single incident occurring, and being able to define what is the effect of that specific incident and understand then the behavior of all the trains.
Okay, yeah, and I can see that is a problem, but then how can we ever know that any micro simulation tool has been validated?
Well, you can run stochastic simulation, so massive simulations with some distributions of delay that you have recorded, for example, from real operation, and you can compare, for example, the overall aggregate punctuality that you have from real operation, but that requires a massive simulation maybe of the whole network or of specific lines.
Okay, thank you. Now, I know in Denmark you think you have problems with the reliability of your passenger railway network. From a UK perspective, maybe your reliability problems aren't so great. So how would you generalize some of the findings from your Danish case studies to be more transferable elsewhere? What would be some of the key messages, key practical messages that you would give to railway operations planners elsewhere from your thesis?
I would say that one of the main findings is about how much timetable slack we should allocate to the resources. And this was shown in the case, but I truly trust that it is a general phenomenon that too large timetable slack is not productive, and it's even dangerous towards the reliability. So I would say, rather than increasing the timetable slack, if we have issues with the reliability, rather go to the solution of the processes, to the identification and solution of the processes that generate delays, instead of increasing the variability of the journey. So the variability of the recovery, rather than just extending the running time, keep them short, but either allocate better the distribution of the running times or the running time supplements, or look at the specific processes that generate delays. This is what is actually improving the reliability, rather than faking the passengers, saying that more time is necessary to run a specific section, whereas it is not true. We are just adding some timetable slack that does not help eventually.
So does this apply to both running time and station dwell times, or just running times? Your generic advice?
Well, I would say it depends. It applies to both. Something that we could do at the stations, for example, is to apply some improvement on the passenger boarding, the processes. So if we have, for example, panels that illustrate where the doors will be, then we can reduce the variability of the dwelling time, because we know that the passengers, that the boarding and alighting will take shorter. Or we can even have hostesses and stewards on the platform to guide the boarding and alignment processes. So I would say that there's room for improvement of the processes in the overall production process of the railway transport, both in the running times and at the stations.
Okay, thank you. All right, we'll move along to the third examiner.
Thank you. I'm going to put this here. Just let's see. Is it working? Good? Okay. So it's also my pleasure to be here. I'd like to say that I also I learned a lot with your thesis, because it's, as you know, not my main area of research. It was also challenging here and there, as Johanna also mentioned, some concepts that could have been more clear, you know, for people like me that don't know what some of these variations of the concepts mean. But overall, it was an interesting document to read. I will focus mostly on the last part, as you would guess, because it relates more with my area. I do have a comment that relates with a question with the discussion before about computational resources, because you said that you could always you know, expect that this growth of computational capacity would solve the problem, and I respectfully disagree. First of all, because the Moore's law makes people think, well, first of all, it's kind of reaching a plateau, so, or at least it's not as growing as it was. And second of all, there are certain types of problems that are simply computationally non-tractable, right? I don't know if this one is one such problem. So that's my first question. In terms of the simulation, you were talking about 5,000 simulations for 5 scenarios.
Yeah.
And do you know how the complexity, how the time of the duration of a certain scenario grows with what? Is it with the number of trains involved, bus lines, stops, segments?
Yeah, it grows for sure with the items simulated. That means the number of trains that are simulated, the actual length of the line, how many signals we have. And it also depends on the amount of output we require the software to write. So we can also shrink that only to the specific times we want. It grows with well, mainly it grows with the number of trains that are simulated.
Like linearly, you have an idea if it grows, if you add one train?
Well, this is more a guess,
yeah, okay.
And I would say it's linear with the number of trains.
Okay.
But I would say this is really a guess.
Okay. Well, if it's linear, still manageable, and indeed you could parallelize still. Okay, so moving on, one general comment on the presentation versus the thesis. I really liked the presentation because it was very visual, and there were things that you were saying, so there were some images that you were presenting that I wished I would have seen them before.
Okay.
So this is a general comment that also, you know, in the introduction, for example, you could have used more images like those that you ended up doing. And clearly it also showed, even the choice of the images and the way you talked about them, it showed that you know exactly the concepts very well. You just need to work on understanding the communication of that. Okay, so moving on. So on paper 4, I don't have many questions. It's quite a short paper, indeed. It was interesting for me to know the concepts, indeed. But I felt that the analysis was very interesting. But I felt that you were good in understanding the problem, but not in getting a scientific contribution, something that you could generalize, okay, on that particular paper. Then I was hoping that, okay, fine, it's an exploratory paper. Then I was hoping that you would use that knowledge for paper 5. And what's the relationship between those two? Because you don't even cite paper 5 doesn't even cite paper 4.
Yeah, well, it is true. The main connection between these two is the identification of the pattern, some recurrent delay, some recurrent development of the delay, as I mentioned, from early trains to reach the final station, eventually even late. And that was more a trigger between the two papers. The reason why this is so short, is also for the limitation of the conference. But this does not mean that it shouldn't contain some scientific contribution. I agree. I would say that there's also Yeah, the main contribution on this is the understanding of the variability of the recovery, and it links to the fifth paper because of the understanding of recurrent patterns or identification of this pattern. It was more a trigger to start the final paper.
Okay. On the other hand, paper 5 it has much more depth. As a clustering study, I think it's pretty fine, the options you make and so on. I do have a few questions. One of them is about the way you evaluated the clusters. I was a bit, at some point you say that there is no, that the choice of the number of clusters, the choice of value of k, is quite ad hoc. Or at least, I don't remember if you used that expression. I don't think I didn't copy-paste it here. But did you use any sort of method for evaluating clustering? You know, silhouette, distortion, the elbow function?
Yes, we did use the silhouette method. And other comparison between the distances between the variance within and between the clusters. Those results were quite disappointing because they were all pointing at the existence of just one pooled cluster.
Okay.
Nevertheless, we could see that there are some patterns that are visible, and the point is that delays in general in railways do follow a continuous distribution. So I would say that there's some influence on the high variability within also the clusters. The way we compared the number of clusterings was comparing the results and from different discrete choices of number of clusters, and then to pick the best fit, especially when there was the phenomenon of splitting the same clusters, like when increasing the number of clusters. Sometimes we could see that the result was actually, the result of one more cluster was that one of the previous clusters was just split in two, and the two clusters looked very similar to each other. So we picked the highest number of cluster for every specific case, where we did have very different clusters.
Okay. So one thing that feels obvious to me is that you have a very high dimensionality of your vectors. So how long was each vector?
This is 19 variables.
19 variables. Okay. Well, it's not that high in that case, because one issue with the silhouette may happen if you have very high dimensionality, and when you compare different vectors, you're comparing so many numbers that the main differences between them are somehow, mixed with the rest. So, for example, you have in the cluster 3, you have this in the which station? K, is it? Yeah. There's this big jump.
This one?
Right. There's
this is
two of them.
support.
Yeah, the one before. You have a big jump. That one. This seems like almost an outlier.
This one. Yeah, this is an outlier actually.
And there's a few of these cases that sort of make me think that if you use some dimensionality reduction technique, you might see some more homogeneity, or at least some patterns that would be, the clusters could separate. But with only 19 dimensions, I actually am not sure. Maybe the results would be quite similar in practice.
Can I add some comments about the dimensionality? I also started applying this exact same analysis to other train categories on other trajectories, and in particular, I started focusing on the Lunto, the long-distance trains from Jutland to Copenhagen. And in that case, I decided to only look at the stops. So on a long journey, we have only Vejle, Fredericia, Odense, and then maybe Høje-Taastrup sometimes, which reduces the dimensionality in just five the variables. Yeah. I would expect to see clearer patterns, clearer clustering but eventually it was not the case. I could see that the continued, like the variability of the recovery would make the clusters look similar anyway. Like I could not see some improvement in using standard methods.
Okay, so now for a more tricky or philosophical question eventually. You say at some point in the literature review, say the downside of neural networks though, this is in page 128, the downside of neural networks though is the risk of data overfitting. Quite true. Reducing the prediction capability, although this risk is lower in neural networks than in simulation models. There I jumped in my seat.
Yeah, this is more a citation.
Why do you say that?
This is more a citation of that specific model,
Okay.
of the specific paper that was mentioned at that point.
Okay.
That in that case, they found that simulation would have this issue with this issue that could be overcome with the neural network about overfitting.
Yeah. Okay. So because I mean, even in the neural network, if you keep adding neurons in the hidden layer, and this is a simple one, I think, you definitely can overfit dramatically.
Yeah.
So, and with the simulation model, you can simplify it also, right?
Yes, that was actually, yeah, that was the result from that specific case. It is true, like, and that's also true for the microsimulation models. Actually, you can easily reach the overfitting of your specific model, than actually losing contact with the real case.
You also say something intriguing at some point, because you say that, and I think this relates with the choice of L1, L2, and whatever other metrics you used. Because you say that k-means procedure tends to generate spherical clusters of some radius. In the case of L1, this idea doesn't make that much sense, unless, I mean, I don't know which space you're thinking of, because if it's in a Euclidean space, then the L1 will make a diamond.
Yeah.
Right?
So yeah.
So
well, I kept the word spherical, meaning the same concept in different.
Symmetric.
What, sorry?
Like symmetric
Yeah.
shape. Okay. Okay. So in terms of it was already asked about the different cases, the fact that you have basically different cases in the different papers. I understand your argument, it makes sense, but wouldn't it still be possible for you to bring along at least some cases that would be, common between different papers, just for the sake of both the sort of the story plot in a way, but also for comparability, because you actually know, you reach the end of your thesis and you know very well many different cases, right? So for example, this one, would you have data from Netherlands to do the same clustering?
Well, to be honest, it took 6 months to reach this data from Denmark, and I would say that, and that was a partner, an industrial partner. I would say that receiving data from another country for research purpose, that would be really tricky.
Okay.
I would instead move everything towards Denmark. I would agree with this argument. The choice was more given by how the research developed.
Okay. So, out of curiosity, how are the rail simulators? I mean, you kind of discussed this a little bit, but I didn't quite understand. How do you actually calibrate the simulators?
Well, you can do it comparing the distributions of input and output.
Sure.
In other environments. You can, for example, you can simulate stochastic primary delays or stochastic incidents, which you can which you can have measured in real operation. And then you can measure the output. So what is the, with some statistical analysis, what was the aggregate punctuality of one specific day that you are trying to simulate, or other specific,
But my question is more like, how is the procedure? Do you change things manually, or do you use some optimizer to do this?
Well, it's more a manual process. For example, one thing that is done in the calibration is the calibration specifically in OpenTrack of the performance parameter. That means you give a command to the train to write at a specific percentage of its theoretical capability to match exactly the running time that are scheduled. So on the schedule, this will accelerate and follow the maximum speed in a reduced amount that you decide to match exactly what is the timetable. Whereas as soon as it is found to be delayed, then it will follow the maximum performance. And this is a manual procedure that you do for every single train.
I see. But given your OR skills, would you imagine that there would be an opportunity to do this automatically?
I think there would be, but there's a little too much complexity to do this in an efficient way, I would say.
Okay.
Because there are all the individual trains that can be triggered, that can be tweaked, or there are the times that are necessary for individual signal blocks to be freed up after the train passes. There are a lot of individual items that you should calibrate that would take a lot of time. And plus, this is also right for manual procedures. But I would say this adds up too much complexity to be handled by an optimization problem, I would say.
Okay, so I pass it back to Johanna.
I have a question on from your presentation. You claimed that, I think it was related to paper 5. You said that it was concerning the dispatching strategies, that trains ahead of time, they did get another track allocated. It was congested.
Isn't it paper 4 maybe?
Maybe it was. It was a claim from your presentation now. You said that it's problematic with trains that depart ahead of time.
Yeah, so this was the case.
So did you verify that they actually got another track?
No, this is an interpretation. We didn't go and verify we didn't have the data we didn't have the track allocation of the individual trains, so we could not verify this individual effect.
So how did you come to this conclusion then? That
out of experience.
Your experience?
Yes.
Okay. And you didn't speak to dispatchers?
Yes, we did talk not to the dispatchers in person, but we agreed on the findings with the partners in the project, with DSB and Unidirectional, and they agreed that that was most likely the case.
Okay. Because it's a discussion in Sweden now that trains that are ahead of schedule also cause delays because they are in the way. Often it's freight trains. These are passenger trains. Yeah,
this is all about passenger trains.
Yeah.
I should have mentioned.
So it's interesting, I think, if this claim is correct, that even though they depart just a little bit ahead of time, it causes problems along the way.
I would say. Sorry.
It would be interesting to verify if actually it is so blocked that they have to be allocated another track, and is that really a problem for people to move then, or why is it so problematic with another track?
I think, if I can give my personal interpretation of this, is that it depends on the dispatching system. So, for example, at Unidirectional, they are trying to develop in these days what they call the scheduler, which is a live dispatching system that on both the planning phase and on the operation phase, what it does is to assign not a slot, but a time range for trains to run, which means apart from the public timetable, trains are a little more free to travel around their schedule. And what they're claiming is that this system will be able to reallocate continuously all the resources, including the tracks, in the optimal way.
Okay.
This is not really my field, the optimization, so I would not be able to judge how this is possible. I know that there are some concern on the actual possibilities, but I would say that if this is possible, given that this is possible, then the problem with earliness of trains should have a lower impact on the circulation, rather than, of course, the dispatcher has a dispatching strategies. The human dispatching strategies have a hard component of personal experience, so it's kind of more static decisions, like if there are some conditions, then I will apply this, or I will apply other strategies.
Okay, so less stochasticity.
Yeah.
I have one final question, and that is, you mentioned your work in connection to VP5 in IPTOP, right?
Yes.
So I'm just a little curious, how would your analytical model be combined with the optimization? Because I feel that in optimization, it results with a schedule.
Yes.
So it's a deterministic one, of
Yes.
course, but you have then a prediction of how it will look. How will your model play a role there?
Given the timetable, we can simulate some primary delays and assess how this timetable would react to this primary delay. So we could find indices of the sensitivity to primary delay. So we can say whether this timetable would be strongly affected by a known distribution of primary delays. So in theory, what we could do is to find distribution of primary delays from historical data, and then feed this into the simulation or the analytical model to estimate what would be the expected aggregate line delay given the distribution of primary delays. And we could return this evaluation to the optimization.
Okay, so that is not a real-time thing, because you mentioned that it can be used for online. So that's why I was confused.
Well, that's more an idea. It could be given in theory, like if the optimization process, of course, follows an objective function that could generate different solutions, and we could have several methods, different methods that apply this optimization recursively. And if there's a need to evaluate several, let's say we can define the objective function as probably something that defines the relationship between the aggregate line delay and the primary delay. So in this case, we receive a solution, and then we evaluate that for the next iteration of the optimization. That's what I meant, like a
So it's a stability test, sort of.
Yes.
Okay. Mm-hmm. Thank you.
You're welcome.
Yes, I have one last wrap-up question. So this is related to paper 4, but I might be able to bring it back to some of our discussion on papers 2 and 3. So apologies for quoting bits of your thesis to you, but this will help frame the question. So this is on page 117, where you say recurring delay patterns may be found dependent on the infrastructure layout, the rolling stock performance and reliability, the time of the day and of the year, and the stationing on lines and at stations. Now, maybe I'm misreading this, but this seems to be inferring causation here, and it seems to me your analysis in papers 4 and 5 is identifying correlation, and there would need to be further analysis in such multifactorial problems before you could infer causation. I just wondered what you thought about that statement.
Yes, this is true. The inference on the factors should be developed more, and the reason why it was not done is because there was a lack of information or lack of data. The only data that we had was either time-based factors that were basically the same timetable, or the equipment that was actually used in real operation. Now, in this specific case, the equipment was not found relevant. But yes, it is true. We could improve the factor analysis or apply actual factor analysis in this clustering, in the cluster membership, to identify what are the actual causes to develop specific delay patterns. So yes, this is at this point it's more on the correlation between, like the recurrence, identifying the recurrence of some characteristics of the trains within specific clusters.
And therefore, the causation analysis would be, that's under the further research box,
Yes.
is it? Yeah, okay, thank you.
So I just have, I don't have really a big question now. I have more curiosity. So As a resident in Denmark, and you mentioned this a few times, that the railway system has its issues. I don't know if the train that you show is the Italian ones that...
I knew you would catch me on this. Yes, this is an Italian train.
Anyway, so my question is, I understand you're moving on to Bene Denmark,
yes.
Right? So how will this research make a difference there? What do you think will be? How do you make sure to bring, this knowledge, as opposed to go there and
specifically? I would move to the department that is looking at the future. So it's on the capacity development. So it's really based on simulation. So I'm sure that I will be able to reduce the amount of simulation to apply this method, this simulation sampling, to make more efficient simulation. Mm-hmm. I would say that if there are chances that the planning of the future is done also looking at the past, how the operation looked like last year, for example. So, and I would say that the clustering analysis, the delay pattern recognition would really be a support to this improvement, especially because you develop the capacity or the railway line also looking at what you can correct from the past, and in a sort of a feedback loop. So I think that these are the main contributions that can be used straight away from the industry.
Okay, thank you. From us, we will give time for the supervisors.
Yes. Next up is the supervisors having an opportunity to pose questions.
Okay, thank you very much. I will not ask many questions, of course, because we have asked them along the way. I will just, first I will make a comment, because what you cannot really see from all the papers is the enormous work actually to get this data and to understand the data, but not at least to clean this data. So, I mean, there has been a long work effort before you could do this analysis, both building the simulation models, but I think particularly related to this clustering work that, there was a lot of issues that you cannot really say you get academic credit, but you have to do this before you can actually do the work. And that's also sort of influenced the sequence of work you could do, because it was quite late that you actually got this data. I think that will just lead to one comment that relates to the clustering work, and maybe you could put up the figure with where you had the clusters and the delays. Yeah, no. Next one, I think.
Next one, yeah. This one.
This one, yes. So you said in one of the answers actually also that you should not just put more slack in the timetable, but you should actually look at the delay causes and reduce them. And that sort of relates to John's question, because we got this data about delay causes from the Railnet Denmark, but that was also a lot of issues to clean this data. But say that if we have this data in a clean format, so that could be sort of linked to the timetable or each train run, how would you actually relate the clustering results with the delay causes? Because that could actually explain the causal relationship between delays and reasons for the delays.
So, thank you for your comment. It actually opens several answers that I forgot to give before. First of all, I would also say that the choice of the case studies was also linked to the accuracy of data, because we have automatic train detection systems in Denmark only on the selected lines that I presented, that shrank the the opportunity to analyze different lines, and that was specifically on the lines that I presented. And in particular, we also had about this automatic train detection system, we had a bias that we knew about that would prevent us to be as accurate as we wanted on both the clustering analysis and on the running time calculations. So we had the corrected data only for the coastal line that we analyzed in the clustering, and for the other line. Now, just to answer this, it is true, we do have codes for delay causes from the dispatchers. First of all, there are issues with this because every country has different forms of registration of these causes. So, for example, in Denmark, we have one cause of delay, one delay cause assigned to all the records of a specific train that exceed one delay threshold. So this does not explain what is the increase of delay. You can only explain what is the total delay according to the dispatcher's interpretation. Whereas in other countries, you have a delay cause that is assigned for any delay increase of above 1 minute. That is much more accurate information that can really help the data analysis. I would also say that in other countries, both in Norway and in the Netherlands, some big data analysis, some delay trees were used to identify where the primary delay in realized operation, and these delay trees could be connected to either conflict of circulations or other types of primary delays. And this highlighted that the manual registration of, the manual recording of delay causes is not accurate enough to apply analysis on the data. So there were too much variability. So there were actually too many wrong allocation of delay causes in the process. That means that this could be, in this case, we did not validate the Danish data, but it could be that actually the dispatchers are not accurate enough in this evaluation, both because they are assigning a delay cause themselves, and also because in a large share of the Danish network, they are even recording the time of the trains, the timestamps manually, which means that there is a low accuracy in several points. And that's also why on the whole journey from Jutland to Copenhagen, I could only use data from Vejle to Copenhagen.
So maybe now you get a job in Railnet Denmark. I think there's some issues with the practice, right? Because, I mean, if you ask the general public or the politicians, they are very dissatisfied with all these delays. But then, as you say, that the rail authorities, they don't really register why, the causes for the delay accurately, and they don't know really why the trains are delayed. So, I mean, then it's also difficult to do something about it. So I think there's a lot to do actually on just measuring delays that you could take with you to Railnet Denmark, because, I mean, if you don't really know that, it's difficult to do something about it.
Yeah.
Then I had another comment to this figure also, because you said the thing that it's not a good strategy just to add timetable slack. But if I look at this figure, I think that the timetable slack is maybe not put into the schedule in an intelligent way, right? Because if some stations, all the trains in all the clusters, they are all delayed systematically, so it seems like there's not enough slack at these stations. Then you have some stations where the trains are never delayed, so maybe there's too much slack. And then there's some stations where they catch up, so that also indicates that probably the timetable should have been different. I don't know if you have some comments to that, or how you would actually... I have a
comment on this specific point, and this is, as I just mentioned, we got some correction factor for the delay records, which were based on the track circuit. And that means, in general, before the correction, the data that we got meant that it resulted in early arrival records and late departures. And that's because how it is measured. Bene Denmark and DSB applied some correction factor just recently in 2016, whereas this data is from 2014, where they calculated the deviation, the systematic deviation between the recording from the track circuit and the actual position of the train using the GPS data. That means that Norrport, which is this station, which is the only underground station, could not be measured with this because it is GPS based. That means that these specific records are recorded, the trains at this specific station are always recorded late departing and early arriving as compared to the others. And this is the bias that we have on this station. Other than this, I would say that the increase and decrease of delays is actually always, on average, around 1 minute. So I would say that in this specific line, this misallocation of timetable slack is not visible, at least from these statistics. We might relate it also to other factors. One thing that is important to mention that appeared also in in prior literature is that not necessarily in standard or recurrent increases or decreases of delay correspond to misallocation of slack. It could easily be linked to other causes of delay. And what I'm referring to is specifically to bus networks where systematic delays at the beginning were tackled moving the allocation of running times, but they were found eventually linked more to other factors. So it's more a causality analysis. We should also consider this available running time supplement in the causal analysis in further research.
Okay, thank you very much.
Thank you.
Pass it on to you.
Thank you. So thank you, Fabrizio. And one important part of being a researcher and of being an engineer is communication. And I'd like to compliment you on your presentation, like I think also Johanna, maybe was it Francisco or both, that you really in many ways presented pictures which could have benefited before, but there's always, of course, a time delay, but you managed then to use the time after handing in the thesis to continue working. So I have one thing I'd like to discuss. Wonder if you go back, just one slide back, and take this picture of the cluster delays. So I would like to hear a little bit about your opinion. I mean, it's something we have discussed, but if you can elaborate a little bit of what you think you achieved with the cluster analysis with respect to previous methods. So what is it that we see and can explain? And then I would also like, which is kind of a hidden question also, but I'd like to also hear you elaborate a little bit about what there was not time enough within resources. It would have been very, very nice also to get out of the clustering, I mean, in your opinion. Of course, I have minor opinion.
So first of all, I would say if we compare these clusters with the pooled dataset, this is the same exact dataset, but this is how it would look like if we looked at it in a pooled way. If we calculate the average of this, then all the distribution would sum up all together. And we could not see the effect of, for example, these trains that are being delayed. We could not see them in the pooled dataset if it was also overlapped at with these trains or these other trains, because then the average would be lowered. So the increase of information that we reach by the clustering is that we can identify patterns, something that happens recurrently but would be hidden by overlapping different patterns at the same time. And this is mostly visible with the delay change profiles. Here I compare the average of the pooled dataset with the averages of the individual clusters. And you can see that, for example, here one of the cluster has actually even the average of opposite sign as compared to the others. And we could not see this at all in the pooled dataset. And also in the paper, what we see to show the gain in information is the comparison between the pooled average and the averages of the individual, or average, median, and all the percentiles, with the respective percentiles related to the individual centrality. This is the main gain of information that we can get. What I would say that, yes, it is true from this cluster analysis, if I had more time, I would go farther with the causality analysis. I would try to understand what are the factors that rule the cluster memberships, so that we can already include in this systematic analysis the identification of the reasons why there are some systematic delays so that we can tackle them already in this phase. Whereas now, at this point, we can identify that there are recurrent delay patterns, and we can try to observe what is usually done in real operation is that you observe, you put specific focus on some part of the operation to understand visually, basically, or from experiencing the operation, what is that systematically happens to generate those delays.
Yes, so that's all. But Mike, if you go back just to the other slide again, also as I remember, Fabrizio, and here my memory might fail me a little bit, but you found in the finalization of paper 5, you found some previous work, which, according to my memory, were people doing kind of trying to understand this kind of data, but they were kind of station specific and so on. So what I think that is the contribution here also is that here there's the whole spatial dynamic. So rather than just looking at one station, we also, the clustering is trying to take the whole track. So there's some spatial correlation, which also leads to what I think could be very interesting to pursue, and that's the time dynamics, because these are not really independent observations. So when we cluster, we would usually assume that we have independent observations, but we do not. So in that sense, we make a huge methodological error if you want to excuse of something. Well, you have to advance and so on. So the next thing, which we have also, we tried, but didn't have time, and it was difficult, all those space-time diagrams which we were able to, so one could start to classify days or classify periods, and that's one, to the extent that Bain Denmark will allow you to have time to continue, that's something I think could be worse maybe to pursue in the clustering, to really put the clustering in further, and yes, so. Thank you.
Yeah.
Yes.
I would just like to add, yes, it's true, we started doing this, and I would say that the good way to start this, or the feeling on how it should be done, is to calculate the average delay over time period, so that you can apply some time series analysis in this. So it's basically trying to predict the delay in the past operation, and then you can find some correlations with the factors.
We have one more supervisor. First tips on questions. Yes.
Thank you, Fabrizio. My first question, I'd like to have you bring up the slide where you show the sample data and you calculate the 2%. You calculate the 2% cutoff of the where you calculate the run times, I believe. Yeah, this slide. How sensitive is the analysis to the choice of where you draw this cutoff line, and how important is it to get this correct?
Well, this is more, this cutoff was an interpretation of the data, so it's more that's more the result. So we decided to take this second percentile because of the large difference between the actual minimum and the second percentile. And we actually interpreted this. We didn't verify this, but we interpreted this as some systematic errors, some errors in the delay detection, in the train detection system. It would be really unlikely that one train out of 100 would be able to perform this, and all the others would perform this constantly with this level of running time. And that's also confirmed by the other stretches that are represented here. These are diagrams of running times through different stretches of the same journey. And you can see that the first one is very constant. There's basically no variation in this running time, whereas here, this large variation in just 1 percentile is, it does not look reasonable.
So how do we mass produce this if we want to scale this up and do many data sets? How do we speed this up so that we don't have to manually examine every one separately and check
there
this
might
by
be
hand?
some systematic analysis of goodness of fit, for example, of the assumed distributions of running times. We could analyze the distributions of running times on specific sections, and we could identify what would be a good a valuable goodness of fit test for these distributions. And
Okay.
this is what also I think our master student did in a part of his work in his work on Cuspin,
Okay.
I guess.
Okay. My next question, or last question, is if you go to the comparison of your cluster analysis slides, and in this comparison of the average versus the 5 or 6 clusters that you identified, the bar chart, that one right there. What would be necessary if I want to create a dynamic dashboard? If I would like to create a system where I could be in the office at Bain, Denmark, and I could pull up on my computer screen this picture, and it was live. It was today. What would be necessary to do that? What would be necessary for me to turn this into a management tool that I could actually use on a regular basis?
You mean to analyze the operations from today?
Yeah. If I want to, because this is static. This is an analysis of some data from years ago, and was created over a chunk of time. But if I'm in management and I want to use this theory to actually gain insight into what's going on, I don't know, maybe from this morning, or even possibly live, that is, with a mix of the current data from the last few hours and some kind of projection forward into the next hour. What would be necessary to do this?
Well, I would say that this particular method is more for past operations analysis. I wouldn't use this on live applications. I would rather use what is under development on very many operators, which is delay prediction. So you have the same, you can apply the same structure of visualization and apply the prediction of delays throughout the day. I would say this would be a better fit for this purpose. You could still apply this, but then if you're, for example, in the morning, then you would only have 10 trains arrived at the destination, and you cannot analyze the trains if they're not arrived at the destination, because you would have a partial data set. So I would say that this particular method does not really fit with the live application. And you can have several different boards. What you could do, for example, linking back to what Bo was saying, is that you could try to apply this kind of clustering to multidimensional data sets, where you both consider the time relation and the trains. So basically what you're doing is to cluster the days of operation. So you can say, okay, this is the typical day where we get delays at this station in the morning. Or you could say, this is in the afternoon. And this is what we started trying to do. And after you've done that on past operation, you can identify the factors that influence the cluster membership of individual days. And you can use these factors. If you have those data available in the morning, then you can say there's some likelihood that today belongs to this cluster. And you can try to predict what it is going to look like at the end of the day.
Thank you.
Thanks.
Thank you for the questions so far. And now I will open up the floor for questions. Do I have any takers? That appears to not be the case. Then I'm going to outline shortly what will happen from now on. The first thing that will happen is that our assessment committee will go into a meeting room and discuss their final recommendation. When they come up with it, this recommendation will be forwarded to the local PhD committee, which will make a recommendation for the dean, who will, if the recommendation from this assessment committee is positive, award the degree on behalf of the academic council. But if there's no further questions, then I will declare the defense proceedings for concluded. And I will invite you to join us in the lunchroom in 116 for some refreshments. Thank you.
Thank you.